Hello, you can hear me? All right. Um, well, first of all, it's a pleasure to visit BIMSA for the first time, and has been an exciting week in Beijing, including the opening ceremony, where we see Richard got awarded the Lifetime Achievement and for his work on the Ricci flow. So I'm particularly honored the father of Ricci in the audience, and also other teachers and friends like Professor Leon Simon, Professor Futaki, and also Ben and many others. Very good to see you. So, following Professor Hamilton's talk yesterday, quickly go over some of the singularity of the Ricci flow, and then it's tied with the Ricci solitons. Ricci solitons, also introduced by Professor Hamilton in mid-80s, singularity models. And so first, here is the plan. So as background, I'll talk about the Ricci flow and the finite time singularities. And then we introduce gradient the Ricci solitons. And after surveying the development and the results for the low dimensional case, we'll start to focus on four dimension, and particularly the concept of positive isotropic curvature that Professor Hamilton touched yesterday. And then especially in four dimension, we can talk about a half positive isotropic curvature, or half PIC, and to look at the four-dimensional gradient, the Ricci soliton with half a weakly PIC or non-active isotropic curvature. And then the last part, I hope I have time to touch at least briefly, is variational structures introduced by Perelman, and then the linear stability becomes an important issue. Okay. So first of all, as you already heard yesterday, the Ricci flow that introduced by Hamilton is the parabolic equation that involves the metric by minus twice of a Ricci tensor. And that's, so as he pointed out, the curvature is second order derivative. So this is a second order parabolic system, weakly parabolic. And indeed, it is the natural analog of the heat equation. And in this case, minus twice of Ricci tensor turns out to be precisely the Laplace of the metric tensor if we use the harmonic coordinates. And the curvatures are all evolving in sort of reaction diffusion equations. And this is what Professor Hamilton also introduced. The curvature tensor is set by the heat equation with the lower order of quadratic terms. We'll look at the three dimensions and the four dimensions more precisely later. Okay. Here is sort of a picture that's showing if we start with the Einstein matrix, then in the positive case, it will just shrink because minus sign in the front of Ricci, like a sphere shrinks to a point in finite time. Or if its curvature is zero or Ricci flat, then it will be steady solution, so remain the same forever. And if it's in a negative curvature like hyperbolic space, then will expand, right? So again, so these are clearly the case. So here's the very first Hamilton seminal work, that well-known three manifold with positive Ricci curvature. So actually, in '82, I was first year grad student at Princeton, and the spring semester, my first year, and Professor Yao invited him to come to Princeton Institute, give a talk, and I barely know. I actually didn't know what the Ricci curvature is. I heard the name from Ben Chao, my fellow first-year student. So his title was Three Manifolds of Positive Ricci Curvature. So halfway through, I said, gee, I haven't seen the first example yet. I thought it was three manifolds of positive Ricci curvature, three examples. So you see how naive I was and how ignorant and yes, and here even no way to compare with Yao's children, college student, but even just a regular undergraduate student at the time. So anyway, as Richard said, let's go anyway. So shortly after his talk, Professor Yao asked me and Ben Chao to study this and try to present in 2 weeks, and that was the real test to come. So anyway, so I think I could also use Andrew's spirit. Let's go anyway. Yeah. So back to the three manifold result. Now I think this is the well known, and say if you start with compact three manifold positive Ricci curvature, then under the Ricci flow, that the metrical remains to have positive Ricci curvature, and after rescaling to keep the same volume, there converges to the positive Einstein, but in 3 dimensions, that's constant sectional curvature. So as a consequence, we know the underlying manifold is diffeomorphic to a quotient of S3. And so that's up to now, this is still the only method, the parabolic method, to give such a proof, and there's no elliptic proof yet after more than 40 years. Anyway, so the Ricci curvature seems to like the positive curvature better in the sense that many positive curvatures are preserved and start with scalar curvature for all dimensions, and Ricci curvature, as we mentioned, is in 3 dimensions. Curvature operator positivity is preserved in all dimensions, bigger than, because the other certainly it's true, so for dimension 4 or more. And more interestingly, there's the notion of positive isotropic curvature that we're going to introduce later on. Is also preserved for all dimensions and start with Professor Hamilton's work in 1997. And then the higher dimensional, much more technical proof is by Simon Brandler and Ricci, and at the same time by Nguyen, from back then was from ANU, a student of Ben Andrews, former student. So what the Ricci flow can do in differential geometry, these significant results are related to differentiable sphere theorems. Start with Hamilton's work in 86 in dimension 4, and then later on, after almost probably 20 years, by Böhm and Wilkin for higher dimensions, which says if we have a compact remaining manifold with positive curvature operator, then under the Ricci flow, you will also, like in 3-dimensional positive Ricci case, that evolves to a constant sectional metric. So the underlying space will be diffeomorphic to a quotient of sphere. And the other very significant application of Ricci flow is the well-known now by the quarter-pitch differential sphere theorem. This is a very old conjecture by, back in the 50s, saying if you have a compact manifold with global quarter-pinch sectional curvature, then the manifold should be diffeomorphic to space form. And so in that case, the homeomorphism was proved by Marcel Berger and Klingenberg independently in early 60s. However, the argument using geodesics and injectivity estimates also only came to the homeomorphism. So it was much later using Ricci flow technique to actually also the condition only needs to be pointwise quarter pinch. For dimension 4, actually, it was proved the first by Hai-Wei Chen shortly after Richard's work on 4 manifolds. So here, the key step is a curvature pinching estimate. Essentially, what here shows that as when you start with a positive curvature or curvature operator, or the thing is to become staying positive curvature category and start become round. So it's the roundness estimate or curvature pinching estimate. Now, of course, the major application to topology, as we all know, is 3-manifold topology, Poincare conjecture, and Thurston's geometrization conjecture of a program that Hamilton worked on for over 20 years and finally completed by Perelman. So what involved, roughly speaking, is 3 major steps. The first is determine the structure of singularity. We're going to see what the singularities are, what they are. And once you understand the singularity, so this is quite crucial that we know what singularity types are. And once we know that, and then turns out in this case only if cylindrical singularity, the next singularity is essential. So you have a cylinder, so you can do connect sum and surgery. So the second step is perform surgery and show the discreteness of surgery time. And the third step for Poincare conjecture is using finite extinction time. And for the geometrization, you have to understand long time behavior. But the first key step before anything else is determining the structure of finite time singularity. And this is what I'm going to concentrate on for next 10 minutes or so. Okay, yeah. Well, what is the finite time singularity? So suppose we have a compact manifold and we run the Ricci flow, and suppose when t approaches certain finite time capital T, the curvature is going to blow up. So curvature blows up in finite time, and that will be called finite time singularity. According to Hamilton, in the compact case and finite, and you have only 2 types of singularities. If you allow infinite time and non-compact, there will be a type 3 singularity. So the first type is similar to the sphere shrinks to a point. The curvature blows up in the rate inverse proportional to the time remaining, like sphere shrinks or cylinder shrinks to line. And second time is otherwise. Okay. Now here are 2 sort of intuitive examples. The first one is the now well-known called the neck pinching. And in early 80s, shortly after Hamilton's first paper, Yao pointed to him the neck pinching phenomenon. So that's essentially it's dumbbell shaped, and you have a small sphere S2 cross interval, and that small sphere have a lot of curvatures. Even though this has a little bit negative one, you will have still positive scalar curvature, and then you will pinch towards there. And later on, of course, we talk about we can do blowdown argument. That this is the neck pinching phenomenon and rotational symmetry. And the second is, as Hamilton then quickly observed, that you could have a second degenerate neck pinching when the dumbbell is not symmetric and you have a very delicate shape just right, then actually you will pinch towards that shape. If that's the case, then later on the blowdown argument do and also going to so-called brine soliton. Okay, all right. So the method is like in all PDEs, when you have something blowing up, is we do rescaling, okay? So in this case, using Perelman's non-collapsing, crucial non-collapsing estimate to get injectivity estimate and Hamilton's compactness theorem, we could do a sequence of dilations and take subsequence to converge it to a limit solution, and always possible. Yeah, if we work on initially the compact manifold particularly, and that's sort of schematic picture. So if you have neck pinch, and as you pinch almost the sort of you do rescaling, you will get something like neck. Okay, so what are possible singularities? Turns out, it turns out there are two types. So type 1 corresponds to shrinking gradient Ricci solitons, and type 2, oftentimes leads to steady solitons. Not always, so steady solitons always more subtle. And sometimes we also say Ricci soliton singularity models, because these definition doesn't have to come from dilation limit. But if the stick quantity comes from dilation limit, that will be called the Ricci soliton singularity models. More generally, we get ancient solutions, the dilation limit that exists for all time in the past. So the ancient solutions are more general, and the most significant ones are shrinking steady solitons. Now, in the first one that Hamilton showed using his differential Harnack and Hamilton IV pinching, saying is any type 2 finite singularity model in 3 dimensions is necessary a steady gradient Ricci soliton. So 3 dimension, because we'll talk about Hamilton IV pinching. On the other hand, the Perelman doesn't distinguish the types. So for every finite time singularity on compact 3 manifold, when you dilate and you can do blow up, and then you do blow down if necessary. You will eventually always ends at a shrinking gradient sorting. Even the degenerate neck pinch, you have something like a parabolic shape at the infinity, which is brine soliton, but then you can blow down. If you look at the infinity, it will be a cylinder anyway, so back to the shrinking soliton. So in higher dimensions, as we said, that not always true, and the one case you can conclude the type 2 singularity model is by, again, Hamilton's work using Liao-Hamilton's estimate, and you get to the steady gradient solitons if the curvature operator is non-active. And however, for the type 1 case, turns out the dilation limit is always a shrinking gradient soliton. No curvature conditions needed, unlike the steady case. So this is the work of Neighbor and followed by Anders Miller-Toppin. And I think at the same time, Huai-Dong Cao and Zhang Qi also proved the similar results. So in the conclusion is, if we have a compact manifold and you have finite time type 1 singularity of Ricci flow, then the dilation limit always leads to shrinking solitons. So this is the most important one, generic case in some sense. So what it is? We have talked about the gradient Ricci solitons. So gradient Ricci soliton is special remaining manifold together with a potential function on it, so such that the Ricci curvature plus Hessian of the function potential is proportional to metric. So this is similar to Einstein metrics, except we have a Hessian of a function. And then like the positive, negative, or Ricci flat, we have shrinking, steady, and expanding ones. And the general Ricci soliton is not a gradient vector field. You have vector field, you take in lead derivatives. But most actually the type 1 singularity, type 2 singularity, finite singularity always is a Ricci soliton. But type 3, you could be ends up non-gradient ones sometimes. So, for example, some of the, say, rigid examples, or say, the obvious examples are Einstein manifold, or you could also, the standard, the Euclidean space, you can think about as also Ricci solitons and with the Gaussian, right? So, depends on constant rho, you could make Rn also a Ricci soliton, and then you can do the obvious product. With the matching constant rho, okay? Of course, we'll be interested in non-rigid ones, will come later. So why do we study gradient Ricci solitons? Of course, the most interesting one is the number 2 and number 3. Number 2 says it gives rise a self-similar solution to the Ricci flow, and actually it's, you can use the vector field and generate diffeomorphism, so that's, and you have a scaling factor. So up to diffeomorphism and scaling, it's look like safe, so self-similar. And they, of course, for Ricci flow, they model possible singularities of type 1 or type 2. But on the other hand, for purely Riemannian geometry or even geometric probability theory, Ricci solitons are interesting in the sense that they are special smooth metric measure spaces with so-called Berkeley-Emery, which tends to be constant. And also, you know, there are critical points of Perelman's lambda and mu entropy. So like Einstein is critical points of the Hilbert-Einstein function, and this is something similar. Finally, this is closely related to the important Liao-Hamilton differential Harnack inequality. The quantity vanishes on the expanding soliton. So actually that is what Richard actually leads him to get the precise statement of differential Liao-Hamilton differential Harnack. Anyway, so many other things. All right. So let's talk about the low dimensions now, up to 3 actually now well understood. So first, in 2 dimension, back in mid-80s, Hamilton already classified 2-dimensional ones. So for shrinking one, you only have S2, RP2, or the flat R2. So if it's non-flat, then it must be S2 or RP2. In the steady case, he found this very interesting cigar soliton that is explicitly, so here I'm not talking about flow, it's just the remaining steady one, okay? So just the remaining metric that generates the flow. So here is, as you've seen from his talk yesterday, so actually here potential function is also very explicit. And he showed that that's the only up to scaling the 2-dimensional static gradient Ricci soliton. So 2-dimension, yeah. And non-flat, of course, that you otherwise you would flat R2 will be. Did I add non-flat? Anyway, so here is the picture that cigar. We didn't have a smoke. We should add a smoke solid coming out, Richard. Right? It would be better. So let's see. Do we have the one? And this actually is Lai Yi and her going to be the right nice boyfriend that helped to draw a picture. So I'll ask him to add the smoke next time. And so that's the 2-dimensional cigar soliton. And then the picture is in all dimensions, 3 or more, you have brine soliton, which is rotational symmetric on Rn, opens like a proboroid, okay? But not the cylinder. So the cigar is, in Perelman's terminology, is collapsed. But all high-dimensional brine soliton is non-collapsed. And the, hello? Yeah, did I? Okay, so that's the brine soliton. Oh. Now for shrinking soliton, that takes, so first of all, by so-called Hamilton IV pinching, Tom IV observed that any compact 3-dimensional one, the shrinking one, has to be a quotient of S3. And then the major achievement for in the classification 3-dimensional soliton is Perelman's work. that shows that non-flat three-dimensional complete compact or complete non-compact with bounded and the positive non-negative curvature, sectional curvature, has to be standard. So the rigid examples, either S3 or S2 cross R and their quotients. So those are typically we talk about, right? Einstein ones or Einstein ones cross the Euclidean ones. So, and the improvement was made by Laney and Warwick, just assuming the Ricci non-active and allow curvature to grow. And then also Peterson and Wiley, showing that you have certain integral bound, then that's also true. So these will be weaker than that. And finally, it turns out using a work of Bin Chen, we can remove all curvatures. So essentially, if it's not even the singularity, so Perelman's will be essentially singularity model ones. And then the last one saying doesn't have to be singularity model. Any three-dimensional shrinking Ricci soliton is the standard one, Okay. So that's the shrinking. The steady, as we said, is always delicate and much harder to deal with. And so in 2012, Simon Brander first confirmed what the Perelman claimed, that any three-dimensional at a non-collapse, kappa non-collapse with positive curvature has to be Brine soliton. So this essentially classifies the three-dimensional singularity model of steady solitons, because all the curvature essentially will be automatically true, we point out. And then I think Professor Hamilton made a conjecture, probably early on, right? Early 2000. There should be other, if you are in the collapsed case, so this is non-collapsed, is Brine soliton. But if you allow collapsing, then you should have other ones and called the flying wing. And here is a flying wing. He emailed me, and later on emailed Eli. So, right, Richard, that's your picture that you showed us. So here's a flying wing, a real flying wing, not the flying Ricci soliton. So, but the proof took about 20 years. And Eli, during the period of 2021 to 2023, in a series of three, I would say, really brilliant papers work that confirmed Richard, your conjecture. And in particular, she showed that every three-dimensional non-compact collapse positive curve one has admits O2 symmetry. So in particular has S1 symmetry. And that's a very hard work to show actually automatically admits S1 symmetry or even more O2 symmetry. So more that shows that indeed you have one parameter family of such flying wings connect Brine soliton, which is rotational symmetric, and to the cigar cross R. So you have an angle that's equal to 0 open up until pi. So here's a picture that she helped draw. If your opening angle, like sector taking, is pi over 6, and if you allow angle more, you'll be like this picture. So eventually you can go over the cigar cross R when if you take that equal to pi. So very nice. So essentially we have a complete classification of three-dimensional case, either shrinking or steady collapse or non-collapse. So shrinking soliton always non-collapsed. Now, what made the three-dimension, including all the work, really sort of nicely is the three-dimensional. I would say magic in three-dimension is the Hamilton IV curvature pinch. Of course, lots of other things, but this is one of the most amazing properties that Ricci flow actually that the Hamilton IV found. In this case, the curvature operator or sectional curvature principal sectional curvatures, and those would be Ricci. And what the Hamilton IV curvature pinching theorem says, if you just suitably normalize, which is very minor thing, always you can do, is whenever the negative sectional curvature go into minus infinity, then the positive sectional curvature is much more dominant. So here nu is the least one. So if nu goes to minus infinity, then you get the factor of log factor in the front. So here you have a log factor. So this is, positive sectional curvature is in much bigger. So as a result of dilation limit, as Hamilton pointed out, a dilation limit will be non-active curved. So you automatically in the limit always you have non-active curvature, and what you can do is, so I come back, is the Liao-Hamilton inequality, which is powerful a priori estimates. So it says if you have non-active curvature in 3 dimensions or active curvature operator in all dimensions, then you have this trace Liao-Hanach inequality. And particularly, it shows that the scalar curvature under the Ricci floor is pointwise, always non-decreasing in time. So what's the significance is later time curvature controls the previous one, and in many cases we need the parabolic regions to have curvature control, and now you only need the time slice control, you got all the forward control. So Leon, you like that kind of statement, right? So you get not, otherwise you have to have really parabolic cylinder control, and this says you only need so this is very repeatedly used in the proof of punctate conjecture, or, in particular canonical Perelman's canonical neighborhood. So this is very powerful. Okay, so back to, and also Binlong Chen made a nice extension that any complete ancient solutions in 3 dimensions automatically have this. So that's why the shrinking steady solitons that we talk about in 3 dimensions all have non-active curvatures. So you can do splitting or you have strictly positive curvatures. All right. Now, moving on to 4 dimensions. Well, first of all, there are nice works in 4 dimensions when curvature, sectional curvature or curvature operator is positive or not active. So probably not no time to have them all. However, we do have non-trivial or non-rigid shrinking solitons. And the compact case are all scalar ones on CP2 blow up 1 or 2 points, because if it's scalar, shrinking soliton has to be on Fano manifold. And only CP2 blow up 1 and 2 points allow non-Einstein ones. The rest of 3 to 8 points have to be Kähler-Einstein in the Kähler case. Also, there are 2 non-compact ones. One is called FIK on blow up of the C2 at the origin, and the other one is BCCD, much more recent, almost 20 years later. Very recent. It's also a blow up of CP1 cross C. So interestingly, in all the Kähler cases, you have to blow up 1 point. The algebraic geometry, complex geometry blow up. And otherwise, you do not have a shrinkage. So that's why on Rn or even on Cn, you do not have any non-trivial shrinking solitons. So in the smooth, you cannot do blow-ups. Yeah. Again, so 4 dimension remains question to see if we have any remaining non-Kähler ones. But we don't know. Turns out in non-compact case seems in some sense much easier to handle than the compact ones. One of the reasons it turns out if we have any non-compact shrinking soliton, then the potential function at infinity or many geometric property turns out has to be limited. So for example, my friend Dertanzo in Brazil and we proved in 2010 saying the potential functions has to behave precisely like the potential function on the Gaussian soliton without any conditions. So this says equation is quite special. So if we have such a thing, the potential function, precisely leading order have to be like in the Euclidean case. And Perelman showed this property under the actual assumption that the Ricci curvature to be bounded. So what we do is remove the Ricci curvature bound. And also the volume grows. So these manifolds behave like the remaining manifold with non-active Ricci curvature because the volume upper bound and lower bound precisely behave like a Bishop type volume upper bound or Calabi-Yau type lower bound, which says at least linear, no more than Euclidean. So that's precisely similar to that. So this is coming from the shrinking soliton equation that replaces kind of non-active Ricci. And also the curvature behaves very nicely in a way. So this is the work of Montiano and Jiaping Wang, saying if we have bounded the scalar curvature in dimension 4 only. So previous one are in all dimensions 4 or more, but here is special for 4 dimension. So if the scalar curvature is bounded, then you can bound the Riemann curvature tensor just by scalar curvature. And in particular, if scalar curvature goes to 0 at infinity, then they were able to use elliptical regularity and other things to say they have to automatically also combine with the work of Ben Chao and his collaborators that have to be quadratic decay. So if scalar curvature decay to 0, then of course that implies the curvature tensor decay 0, and then you use the equation to show that actually automatically quadratic decay. So it's asymptotic conical. And there's some work in the static case and in singularity model by Ben Chao, Mike Friedman, and Zhang Yongjia and others, and Chen Bo-yang, Ma Zilu, Zhang Yongjia. They show that singularity model in 4 dimensions, steady soliton curvature tensor is also bounded by scalar curvature. So these are some of very nice properties. Also, there's a nice uniqueness result, and probably Li Yang would like this one that you had proved a very wonderful result for minimal surface. So here is Brad Koshua and Wang Lu. They proved that for any 4-dimensional or higher, 2 complete non-compact shrinking soliton, if they have the same asymptotic cone, C2 asymptotic with the same cone, then they must be isometric. So essentially the asymptotic cone determines the shrinking soliton. So this particularly says the uniqueness you can, So in particular, if it's actually combine the previous work with Montiano one, if there's a scalar curve, you go to 0 at infinity, then there will be asymptotic cone, and then classification reduced to the 3-dimensional link. So anyway, I think I'll have to move fast. How much time will I have? 20 minutes? Yeah, okay. I'm going to do 15 minutes on the PIC and 5 minutes on variation, it looks like. So first of all, so we're going to now, one very good curvature condition is in the sense that the sectional curvature and curvature operating on X is too strong for each curvature. Right? 3-dimension limit is automatic, but for 4 or higher, you don't have that luxury. So here is a very nice condition introduced by Mikhailov and Moore in late 80s, and this so-called PIC, positive isotropic curvature. So first of all, if you have any orthonormal 4-frame, you can form this curvature relation. And of course, for most of people seeing this initially look complicated, but it turns out this is quite natural notion. And if you do complexify both the metric and the curvature tensor, then you can also show that this is related to complex curvature, sectional curvatures. And isotropic, because this is not the Hermitian extension, but the complex linear extension. So you can define the norm to be 0, and that's why called isotropic. Anyway, first remark is this complicated looking condition is quite natural. So it's like sectional curvature, and it's twin brother or cousin. Because sectional curvature, everybody knows, our grad students knows, arises, for example, in geometry, useful is Jacobi equation and the second variation of arc length. So here it turns out that the PIC condition or isotropic curvature condition arises in the second variation if we have maps from Riemann surfaces into the manifold. Look at this energy functional, and the critical point is harmonic, and then second variation formula, you have this isotropic curvature. So it really should go into textbooks, just one dimension higher, okay? And you have also nice, interesting relations that you can talk about PIC1, PIC2, or will you say pick one or toothpick that Richard or Hamilton will call the toothpick, pick two. Anyway, you can manifold across one-dimensional Euclidean line or two-dimensional plane. And if that's pick, you call pick one, pick two. So interesting is the curvature operator positive or pointwise quarter pinch implies pick two, and that implies sectional curvature. So that's why the quarter pinch actually, you do not use quarter pinch, but use the pick two, and that's preserved under the Ricci flow, and that's how Ricci and Brander, use that condition for the Ricci flow. Very clever, outstanding. And pick one implies Ricci positive, and pick only implies scalar curvature positive. So pick is relatively weak and implies positive scalar curvature. All right. So initially that the topological condition they used is the Morse index theory to show that if you have 4 compact manifold or higher dimension, is pick implies a homeomorphic to Sn, and you have other conditions. Yeah. Okay. So particularly I want to point out is pick. Of course, we already see it's preserved under the Ricci flow, but it's also preserved under connect sums. And now 4 dimension, we all know that you have self-dual, anti-self-dual decomposition of 2 forms, and the curvature, Baroque decomposition, and as such, and in particular, now we can define, turns out that the pick C condition corresponds both A and the C matrix in the diagonal in the Baroque are 2 positive. So the sum of least 2 eigenvalues are positive. And now in this case, we can also talk about half PIC is either matrix A or C is 2 positive, right? So pick is both A and C are positive, and half pick is either A or C positive. And we can talk about non-active. And finally, the half pick is preserved by Ricci flow, and that's the first proved by Hamilton. And also half pick is preserved under connect sums. So they are natural conditions. The examples are the standard ones are S4 and S3 cross R. The higher cylinder they are pick. And then CP2 or its opposite with opposite orientation are weakly pick and half pick. And the S2 cross R2 are only weak picks. So those leads to the sort of hole punch that Professor Hamilton talked about. So these we'd like to rule out. We don't know how to do hole punch surgeries. And there are smooth classifications of compact 4 manifold with pick condition. And first initiated by Richard Hamilton, 97, and followed by Binglong Chen and Xiping Zhu, my good friend. And later, Chen and Zhu with Tan completely classified the pick, remove a technical condition on the, yeah. So they are essentially either diffeomorphic to the standard examples or connected sums. So Ricci flow also used to classify a smooth compact four-manifold with peak conditions. So similar to the three-dimensional without any assumption. And Laney and his two foremost students were able to classify solitons and using the quantity that Richard Hamilton used. So now, in remaining a few minutes, first I talk about the main results. We are talking about ancient solutions with half-peak and classifications of four-dimensional steady and shrinking solitons with half-weekly peak conditions. And yeah, so why we do that? The motivation comes from Taub's work that Professor Yao mentioned at the end in Richard Hamilton's talk yesterday. So Taub's back in '92 proved that start with any compact-oriented four-manifold by adding enough copies of CP2 bars, connect sum, then it can kill the W plus, so make it the self-dual. And what Richard proposed to me, and maybe others, is first of all, use the Ricci flow to classify compact four-manifold with half PIC, because PIC now is classified, so naturally you wonder what is half PIC. And that, of course, is much more challenge. And then maybe use the Ricci flow to approach the stable classification of four manifolds with positive scalar curvature. Right? Positive scalar curvature recently very hot topic. A lot of very nice results come out. Here is slightly stronger. The scalar curvature Ricci flow does not seem to improve anything. So the Ricci flow not clear can produce anything significant for positive scale. However, if you add the half-peak, it turns out you can do something more. So here's at least you can maybe not classify positive scalar curvature in 4D, but at least a stable classification. So that will probably be very interesting. And that's why we look at it. So what are the results? The first results is that the curvature improves. So the Ricci flow tries to improve curvature whenever it can. So in this case, it's in four dimension. The PIC or half PIC saying is A and C both, or A or C has the two non-activity, right? So here says if we have any ancient solution, actually it's the matrix is all eigenvalues has to be non-active or positive, not just the sum of the last two, right? So the least one in the definition could be negative, but here says it will be. So it's like a bit like Hamilton IV pinching in some sense. Yeah, and the significance of this result is being too weakly, it's hard to use Hamilton's strong maximum principle. Once you know it's the matrix A and C are both non-active, then his classical now, the strong maximum principle works. And yeah, so that helps to classify, for example, shrinking soliton with half PIC in four dimensions. So we have three types. So either you have strictly half-peak, or otherwise you'll be standard products, and the third type is scalar. So if you are strictly half PIC, you do not get to have to deal with the hole punch stuff as we expect. It's only SNAC and the CP2s. So the scalar ones already classified as, turns out, the compact ones are the tools we talk about, and non-compact one is through the recent work of Kron, Dero, and Sensong, and Barmler, Sifri, and others. And finally, Li Yu and Wang Bing. The combined work that the Li Yu and Wang Bing shows that the only non-compact scalar ones are FIK and the BCCD. So the third It's completely classified, and this is product. So the only thing left was what is half pick. So that's remain open. So I think I conjecture, probably Richard Hamilton will conjecture too, is that should be S4, S3 cross R, or their quotient, or CP2 or CP2 bar. But that remains a challenge. And also, I sort of like to conjecture a version of Hamilton IV curvature pinching in 4 dimension is if you add the pick condition, then the solution should at least have weakly PIC2. Once you have weakly PIC2, that implies sectional curvature non-active, and you also would, the Liao-Hamilton differential Harnack estimate will be true. So I think this will be very useful. But yet, so for steady solitons with half PIC, we have more possibilities. Either you are strictly half PIC or you are Calabi-Yau. That's all the case. And the interesting one in this case, so Richard, you named something called the funny because you got the Iguchi-Hansen, and you said you also not just Iguchi-Hansen. Iguchi-Hansen will be a version of hypercaylus or Calabi-Yau, but you also have the one which is sort of opposite orientation of that, and that is Ricci-flat and self-dual. So if you are Ricci-flat anti-self-dual, that is Calabi-Yau, right? And so that's one. Maybe you thought that is kind of funny, yeah? What leads you to call it funny? Not laugh, unusual. Yeah, this is right. So that turns out it appears in all cases, and then you have reducible ones and product ones. So. Yeah, and interesting will be, so I think I probably have to move on. I have 5 minutes, I think. Yeah. So the 2 other open problems before I move to the variational structure. One is classify 4-dimensional complete non-compact and non-collapsed ones with pick or even positive curvature operator. And I think this includes the Lai-Yi's example in higher dimensions and maybe plus more. But that's still open. And for people in Kähler geometry, we also like to classify complete non-compact static Kähler Ricci soliton, even with positive bisectional curvature or positive sectional curvature. So for a long time, only one such example was known, and that was I constructed in the late 80s, early 90s, and that's the rotational symmetric one on C2 with positive sectional curvature. And actually, shortly, a few years after that, I was looking into the toric ones, but I wasn't able to find the approved existence. But very recently, 2 groups of geometers, one first Pastov and Sifri, and then Chen Boyang, Cologne, and Lai-Yi, they each produced a family of the toric ones on C2 with positive curvature. So, and they are different. So initially I thought, are they the same? But they told me that's different. So I will speculate that probably there's a 2-parameter family of such things, and maybe that's all. And each will be sort of 2 special, one in the 2-parameter family, but that's yet to be seen. Okay, any questions before I move on to the compact case? So I talk about all the non-compact case. We can say a lot more. For compact one, besides the Kähler and besides the one we can say about non-compact complete, we don't have a single theorem just for compact in 4 dimensions. Not a single theorem just for compact non-Kähler one. That says 5 minutes. Okay, good. Any question? Yes. Um, right. Yeah. Uh, yeah. That's right. Very good question. We'd love to see that happen, and we probably will have to rely on physicists to carry out that, or we certainly maybe can have more conversations. And yeah, in some sense, for example, for the say the Bryan soliton or these things is like Schwarzschild solution and Lais non-com, and you also the Kerr solution or those things are a bit similar. Yeah, but yeah. About just the remaining metrics, right? So there you are doing the Lorentzian case. So actually, you reminded me. We had some work on static solitons that actually borrowed the ideas and some works from physics. For example, you have uniqueness by Israel and and that was suggested to us by Ricci, and we were able to use, well, at least the idea, not to the technique, but to the phenomenon to produce something and for steady solitons. I hope we can return the favor. Say it again. You mean the quantity here? Yeah. Of course, I deleted this slice because of time. The slice before this is just Einstein Hilbert functional. That critical points is Einstein metric. So I start everybody in physics and the geometry knows. So I just deleted this morning. Yeah, is that okay? We can talk about more later. So let me. So there's of course the well-known variational structure for the steady solitons. That's the we call the F functional, which is special case coming from string theory. Just have dilaton or nothing else. Here, however, we put a constraint which is non-physical. That total integral, weighted volume is 1, which is not physical, so that destroys physical. And the first variation, as Perelman calculated, is just the static Ricci solitons. And then he introduced the W functional and corresponding new entropy. Interesting is when Perelman visited the US, 2003 April, of course, the F functional everybody can recognize, and he pointed out. So I asked him after at the end of his talk, I said, "Is there any physical interpretation of this W functional? Because F functional comes from string theory, right?" So he paused for a few seconds, said, "This is years of work. Try to understand Hamilton's work." And then he added, "I think I'm his disciple, though I haven't got official authorization." That's what they said. So he spent certainly a lot of work trying to really understand how this. So this is a highly useful thing and leads to the Log-Sobolev and the monotonicity formula. And the first variation is precisely gradient Ricci solitons. And the monotonicity allows to prove one version of non-collapsing. Yeah. Anyway, back in 2004, 20 years ago, Richard and Tom Ilmanen, we look at the second variation of Einstein metrics, but with respect to Perelman's functional. And we have computed the stability or Jacobi operator, which is pretty similar to the classical one coming from Einstein Hilbert functional. But we have a bit different. There's Yeah, you have to add something. So here is the second variation. The only difference with the classical one is here. For the Einstein-Hilbert functional, the conformal one is your always unstable directions, essentially. However, here we have more information. So the third on the TT part is the same, but on the conformal part, there's some difference. So the TT, the transverse trace part, is always Lichnowich Laplacian related. So here is the corollary. It turns out linearly stable with respect to Perelman's functional, if only if, of course, the TT part has the right sign. But interesting is also put restriction on the first eigenfunction at the conformal things, which is in contrast to the classical Einstein-Hilbert ones. Okay, is up, and you have the things, and you can also do the shrink. With my former student Zhu Meng in Shanghai Huasida, we also carried out the weighted version and for shrinking solitons, not Einstein, and we have similar quantities as Cody-Minkowski sort of showed for mean curvature self-shrinkers. And finally, and here's necessary conditions, and I end by putting two conjectures, one from Richard Hamilton. We try to understand four-dimensional, as I said, we don't have a single results for compact four-dimensional or any dimensional, just for the remaining compact ones. However, the generic ones are hopefully linearly stable ones. We couldn't classify compact ones in general. At least we want to compactify the linearly stable ones, because we can always perturb the metric if we interested in topological ones. So here are two conjectures. Four dimension is S4 or CP2. CP2 is weakly stable. And I think that actually Einstein ones has to be also one of the two. So thank you for your attention. Yeah.
All right, so any questions and comments? So let me bring you first the question. So for like the half PIC for the complete shrinking solitons, do we know anything about the asymptotic behavior of such manifolds?
We are looking at the only compact ones. Yeah, of course, you can look at non-compact ones. Actually, the asymptotic, the conjecture is S3 cross R. So, yeah, non-compact will be S3 cross R. So that will be the behavior we expect. Something similar to that, at least, right? Yeah, so, curvature. Mm-hmm.
So, other questions?
Yes.
Could you show us the definition of weakly PIC?
Right. So essentially, in four dimension, PIC says both A and the C matrix are two positive, right? So weakly means non-negative, two non-negative. Four dimension, right? Yeah. Here. Yeah. Oh, one more. Where did it do four dimensions? Here. Yeah. So PIC is both A and the C matrix, which is that part, is two positive. So the sum of least two eigenvalues are positive. So the least one could be negative, right? But the sum of the two will be positive. Yes, should be possible. Yeah, yeah, O can be translated, right? Yeah, definitely. You can, but yeah, you can in term four dimensions. You can. But once one or two, there will be, so in case of this one, that be essentially similar to Ricci kind of thing. That's in 4 dimension, that's all the standard examples we know. Yeah, so the PIC is the fourth sphere or the highest cylinder, as we call it. And half PIC, which is not PIC, is only CP2 or its conjugate. And then this is really weakly PIC is S2 twin and the quotient. That's all. Yeah. Yes. Actually, don't know whether actually is. Good question. Is that's a possibility, or we don't even know whether that actually leads to steady solitons sometimes. Well, the art examples doesn't have positive curvature, so yeah. So in a sense, what I said is that is a sufficient condition, always guarantee. And that was the first, at the very beginning, 3 dimensions is automatic, right? Because the IV, Hamilton IV pinching. 4 dimensions, there might be some work I have to look into whether type 2 ones without the positive curvature thing can lead to, yeah. Very good question, but that would be interesting, but probably not sort of like always like in the shrinking case. Yeah. Yeah. So shrinking one is really nice that really come from every single, one is the dilation of type 1 always is shrinking.
More questions? All right, so if there is no further questions, let's thank Professor Cao again.
Thank you.
So next talk will be at 11 o'clock.